Hi, I'm Michaela, Math 241, Section 12, and today we'll be covering continuous probability density functions in two variables. Okay, we'll be defining a continuous probability density function in two variables, x and y. So, for a continuous probability density function in two variables, the function must be non-negative, continuous, and its double integral from negative infinity to infinity must be equal to 1. So the function must be non-negative because you can't have a probability of nothing. If there are negative values, then the function, those values don't really exist, therefore there's no probability of them occurring. It must be continuous for a similar reason. If there are any jumps or breaks or discontinuity in the function, then there's going to be a probability of it not occurring, and therefore you can't have a probability of nothing. And lastly, this 1 is important with anything in probability. Logistically, you can't have a probability more than 100%. So there's always going to be two factors, like there's a 50% chance and then of something occurring and a 50% chance of something not occurring. Those equate to 100%, which is 1. So we're going to let f be a continuous probability density function in two variables, x and y. We're also going to let alpha, beta, gamma, and delta be real numbers. And then we can define the probability that alpha is less than x, which is less than beta, and gamma is less than y, which is less than delta, equal to the double integral from alpha to beta, gamma to delta of f of xy with respect to dy dx. Alright, an example of a continuous probability density function is the function f of xy equals x squared between the bounds of 0 less than x less than 1 and 0 less than y less than 3. So we're only looking at this probability density function between these bounds. So first, it must be non-negative, and we see that because it is a polynomial to the second power, that it's going to be positive everywhere, because anything squared produces a positive outcome. So this is true. Next, it must be continuous. And we know that all polynomials, again, are continuous because they produce outcomes everywhere. When something is squared, you're 100% certain to get an outcome. Lastly, within our bounds, this function's double integral must be equal to 1 because you can't have a probability of more than 100%. So we have 0 to 1, integral 0 to 3 of x squared, integrating first with respect to y and then to x. This is equal to the integral from 0 to 1 of x squared y evaluated from 0 to 3 dx. This equals the integral from 0 to 1, plugging 3 in for y, subtracting that from 0 into y, we get 3x squared dx. This equals 3x cubed over 3 evaluated from 0 to 1. Our 3's cancel, and plugging in 1 for x, we're just left with 1. Alright, so this function meets all of the criteria to be a probability density function. So let's say that we wanted to find the probability that 0 is less than x, which is less than 1, and 0 is less than y, which is less than x. To do that, we would set up our double integral from 0 to 1, 0 to x of our function x squared, first integrating with respect to y, and then integrating with respect to x. This gives us the integral from 0 to 1 of x squared y evaluated from 0 to x dx. Plugging in x for y, subtracting that from 0 into y, we get the integral from 0 to 1 of x cubed dx. This equals x to the 4th over 4, evaluated from 0 to 1. Plugging 1 in for x, we get that this probability is equal to 1/4. So, this means that the probability within this function x squared, f of x equals x squared, that 0 is less than x, which is less than 1, and 0 is less than y, which is less than x, is 1/4. So overall, we discussed the definition of a continuous probability density function in two variables. We determined how to correctly write the notation when alpha less than x less than beta and gamma less than y less than delta as the double integral of that function. We also looked at an example and proved that the probability within the example of the function was equal to 1/4.